Welcome to this tutorial talk on the principle of Raman spectroscopy and its application in microscopy. This is a quick reminder that spectroscopy is about light-matter interactions. In spectroscopy, we probe differences in energy, differences in rotational energies, in vibrational transitions. This is what we are interested in this workshop. But you can also, of course, probe electronic transitions. So normally we treat the molecule from a quantum mechanical perspective, and we treat the light as a classic electromagnetic radiation. This is an overview of the topics for today. We will start first with the classical and the quantum mechanical basics of Raman scattering. So the discovery of the Raman effect goes back to the year 1928, and it was awarded with a Nobel Prize in physics already in 1930. And you see below one of the very first Raman spectra, in this case of carbon tetrachloride, you see the intense Rayleigh scattering, which massed to the left and to the right. And on the right you see the stronger Stokes scattering, and on the left you see the weaker anti-Stokes scattering. And on the top you see the experimental setup, which Chandrasekhara Venkataraman. So the induced dipole moment is given by alpha times E. So if you take a plane wave approximation for the electric field, then you end up with three dipole terms, each oscillating at different frequencies. The first one is oscillating at omega 0. This is Rayleigh scattering. That's the scattering which has the same frequency, the same wavelengths as the incident radiation. That contains not so much chemical information and therefore is not that interesting to us. The other two terms are containing chemical information since they involve the characteristic angular frequency of the molecule, not only that of the incident light, omega 0. And these are the terms for Stokes and anti-Stokes Raman scattering. They are red shifted and blue shifted with respect to the incident angular frequency omega 0 of the laser. And the necessary condition for observing Raman scattering means that this term d alpha by dq in brackets at the equilibrium position q equals 0 must be different from 0. So this factor must be, this partial derivative must be different from 0 to be able to observe Raman scattering. So the change of the polarizability d alpha when passing through the equilibrium position, d alpha by dq, that's the change of the polarizability with respect to the normal coordinate, at the equilibrium position, so right to the brackets, q equals 0, the subscript means equilibrium position, that must be different from 0. If there, or in other words, if there is no change in polarizability when the molecule passes through the equilibrium position, then you will not be able to observe Raman scattering. Simple examples, the symmetric stretching vibration of CO2, black carbon red oxygen, and you see that the molecule expands and that the polarizability changes. That becomes more evident in the polarizability normal chorded diagram. So alpha as a function of Q is plotted. You see that when the molecule contracts, the polarizability is smaller. You have alpha for Q equals 0, alpha 0. And then for the expansion at positive Q values, it increases. And you see that the tangent, so the partial derivative at this position Q equals 0, that this has a slope which is different from 0, and that's nothing else than this partial derivative. So that is an active Raman active vibration because this condition is fulfilled. Now that's called the selection rule. Good. Raman is routinely performed at the Stokes site, depending, because the vibrational ground state is significantly larger populated than the vibrationally first excited state with vibrational quantum number V equals 1. So Stokes starts from the vibrational ground state, V equals 0. Anti-Stokes Raman scattering starts from the less populated first vibrationally excited state at V equals 1. For quantifying this, you take the Boltzmann factor, so the ratio of the population numbers in the excited relative to the ground state, and that is proportional to Euler number to the power of minus energy difference divided by Boltzmann constant Kb times absolute temperature T. And KBT roughly is 200 inverse centimeter, or 1 eV divided by 40, so 25 milli-electron volt. And these are values which are useful to remember. And another helpful relation or identity is that 500 nanometers are 20,000 inverse centimeter, and that is roughly 2.5 eV. That helps making the communication between chemists and physicists a bit easier. So examples. Sulfur-sulfur stretching, for example, disulfide bonds in proteins occur around 500 inverse centimeter, depending on the conformation, and that means a population of at least 8% in the first vibrationally excited state. Contrast, aromatic CH stretching around 3000 inverse centimeter. Here it reduces to e to the power minus 15. So you won't be able, or you're not in a good position to see anti-Stokes scattering so far at such high wave number values. Simply because the energy difference is so large. No? So the spacing between V equals 0 and V equals 1 is much larger, 6 times larger than for the SS stretch. The quantum mechanical description is written here in terms of the second order perturbation theory, the famous Kramers-Heisenberg-Dirac dispersion relationship. So first of all, you see the formula for the intensity from the initial to the final state. In an approximation, it's proportional to the incident intensity of your laser light, I0. C is a constant to get the units correct. Omega scattering enters with the force power in this approximation. And then you have a sum over all the tensor components for the transition initial to final along all the Cartesian coordinates rho and sigma. And that electronic polarizability alpha enters quadratically. So these are the important scalings. Intensity linear, I0 to the power 1. The scattering angular frequency is entering with the force power, so very strong dependency. And the molecular property of the electronic polarizability enters at least quadratically. And that term for the electronic polarizability in quantum mechanics can be expressed by the corresponding transition dipole moment. So you go from I to the intermediate state R, and from the intermediate state R to the final state F. And the mu are the corresponding transition dipole vectors. So these are the transition dipole moments involved with these transitions. To, in the case of normal scattering, to the virtual state and from the virtual state down. And these two terms in this sum just differ by their or essentially differ by their denominator. So there's h bar omega RR minus h bar omega 0. And for the right term, it's h omega RF plus h omega 0. So there's a difference and the sum. And that becomes important, especially for pre-resonance and especially for resonance Raman scattering, where the incident frequency, the h, or the incident energy, h bar omega 0, the energy of the light, and the energy of electronic transitions, h bar omega Ri, so the difference between the ground electronic state I and an electronically excited state R, in this case intermediate state, are comparable or even equal. Because then this denominator, this difference becomes very small. In the limit it becomes 0, and then because the denominator becomes very small, the overall terms becomes very large. The alpha increases in this case of an electronic resonance, and this is called resonant Raman scattering, or resonance, normally called resonance Raman scattering. So these are two examples. The main advantages are sensitivity. Alpha goes up by orders of magnitude, by several orders of magnitude. That means you get an enhanced Raman signal. You can work even at dilute conditions, so not just millimolar but micromolar conditions or concentrations. And the selectivity increases. You only probe that chromophoric subunit within the entire molecule where this electronic resonance condition is fulfilled, which means there is a band in the corresponding UV-Vis absorption spectrum. That is illustrated here with the example of hemoglobin. In this case, it has CO as a ligand. The heme, these heme units, these cyclic tetrapyroles, have an electronic absorption in the visible. It's a dye essentially, 440 nanometer. There's a peak in the UV-Vis absorption spectrum, while the peptide backbone and the aromatic amino acids absorb in the deep UV, 230 nanometers. So that means if you look on the right, take a laser excitation wavelength at 419 nanometer in electronic resonance with the heme, you only see molecular vibrations of the heme unit. If you go to a much shorter excitation wavelength, 229 nanometer, you see selectively the aromatic amino acids tyrosine and tryptophan. If you go even shorter, 197 nanometer, you see selectively the peptide backbones and phenylalanine. So these are again the corresponding excitation wavelengths.